Okay, wow, things look a little bit sparse today. Okay, so I'm going to go ahead and get started. Announcements for today. Quiz on Wednesday, Thursday this week. A couple people have emailed me to ask what's fair game. Technically, anything we covered up through Friday last week is fair game, so all of the Alkynes stuff, and then there is always the potential for things older than that, like from OChem 1 to show up, but in practice it'll probably be, if it shows up, like the stuff that I covered in the OChem 1 review the first week. Okay, so that's what's going on, and then the sapling due date is going to be 1 week from today because I'm going to cut off chapter 14 today. Okay, questions about that? Okay, cool. So where I left off last time was using acetylides to make new carbon-carbon bonds. Let me fold this down. Okay, so we saw that you can take an alkyne, maybe something like this. You can hit it with sodium amide, or pretty much any base strong enough to deprotonate those protons. But this is like the traditional easiest way. And then whatever alkyl halide you want. And then you can stick on an alkyl group to one end. And then you can do the same thing for the other proton if there is one. Okay, so this is the same reaction we covered last week, so I'm going kind of fast on this. Okay, and then, so you're sort of sticking on up to 2 R groups onto the same 2-carbon center chunk, what's called the linchpin of this molecule, because it's the sort of bit that holds it all together in the middle. And then from here, you can do whatever you want to the alkyne. And that lets you get access to a bunch of other reactions that we may have seen. Like if you turn this into an alkyl halide, for example, you can do alkyl halide chemistry. You can turn it to an alkene, go from there. You get a lot of options. Okay, so I mentioned, I guess, during the OChem 1 review that I was going to sort of maybe tie this back into acetylide chemistry for making carbon-carbon bonds. So I'm going to do sort of a quick, I guess, comparison or contrast between the two methods. So CF compared to cuprate epoxide addition. Which is something Latin that I think just means compare to. Yeah. I don't know any Latin. I just picked it up from bits and pieces. All right. Versus. Okay, so maybe let's say, I didn't explicitly include this in the notes, but it's pretty much a review of stuff that we've seen. So here's maybe butyl cuprate. If we do, say, an epoxide and then our water workup, we're going to get 1, 2, 3, 4, 1, 2 OH. So kind of the key tip-off that we've been doing cuprate and epoxide chemistry is whatever disconnect there was, like wherever the bond that we just made, the carbon-carbon bond, it's always going to be 2 carbons away from an OH. And that OH is on the half that came from the epoxide. Versus, if we're doing CC bond formation this way, our disconnects are here and here. So the disconnect here is it's like right up on the alkyne that you use to make the bonds. Okay, so if I give you something and I'm like, build this carbon skeleton framework, and it has neither an OH nor an alkyne in it, then possibly either of these methods might work, just depending on whether you can take either one of these functional groups you get right after the attachment and tweak it to whatever functional groups you're going for. Or it is actually possible to sort of do like a in-between version of these. Because we've done cuprates on epoxides, we can also do acetylides on epoxides. Because they're pretty good base nucleophiles, and they don't have the same issue that cuprates, or that Grignards and lithiums did, where they're too basic for their own good. So we can just as easily do this chemistry. I'm going to draw a slightly different epoxide just to keep it consistent with what I have in the notes, but really you could do like any type of epoxide for either of these. Okay, so then, and you may want to go through the mechanism if this isn't sort of obvious to you exactly what's going on here. But in this case, our disconnect would be here because we're deprotonating the alkyne and then it's going and attacking the less substituted carbon. And so in this case, we end up with a disconnect that's both right next to the alkyne and also 2 carbons away from the OH. So if you're trying to get something with a bunch of functional groups going on, this might actually be the best way to put things together, because from here you've got control over what the OH becomes, and you've got control over what the alkyne becomes. So you've got 2 what are described as like orthogonal functional groups. You can sort of react one and have it go through some changes without doing reactions on the other, as long as you're clever about it. So both groups in your disconnect. And you can sort of modify both independently, at least in theory. There's some reactions that might mess with both of them, but you got to avoid those. Okay, so questions about that? Okay, cool. So a lot of the reactions or syntheses that we're going to see, either or both of these methods, or some combination of them, all of them will work. It's just figuring out what's the shortest route from the product that you get to where you're actually trying to go. Okay. So, the topic I'm going to cover next, real quickly, is not actually in Loudon just yet. It doesn't show up till chapter 18, but it's so useful as a tie-in to this chapter that I'm just going to do it now. And that is, how do we actually get alkynes in the first place? Okay. So the way that we do this is basically, think of it like a double E2 elimination. So if you remember, for E2 to work, we need a leaving group, and I'm just going to stick with bromine because that's kind of the easiest to get on there wherever we want. So we need a leaving group, and we need a hydrogen. But we need to do this twice. So leaving group and a beta hydrogen on adjacent carbons, basically. But we need 2 of this setup for E2 to happen twice. So we've actually got a couple different options of how to set that up. One way is to have, say we've got a molecule like this. If we want to make a triple bond here, we can have either one pair of bromine and hydrogen there, and then we can maybe do bromine and hydrogen here. So in this case, we set it up so that we've got each carbon has 1 bromine and 1 hydrogen. So if we do E2 first, we could do bromine, hydrogen. Those 2 can eliminate. And I didn't talk about the base that we used just yet. Turns out we actually used the same base that we did to make the acetylide, sodium amide, which is potentially going to lead to some issues, which we'll cover in just a second. Okay, so assuming that we pull off the bromine and the H that I circled there during the first E2, we're going to get to this thing. Cis versus trans, I'm kind of glossing over because it turns out not to really matter in the long run. We'll talk about that a bit too. Okay, and then we do a second, and actually, I guess I can be specific about how many equivalents. And then we can do a second reaction, and I'm going to put quotes around this because it's not exactly E2. Technically, E2 was with an alkyl halide, which is like an all alkane kind of single bond thing. So this first one really is E2. The second one, we're doing it to a vinylic halide, where the halogen's on an actual sp2 carbon. So it's not exactly the same thing, but it's close enough. So this we're doing with another equivalent, a second equivalent of sodium amide. And again, we're going to eliminate these 2 groups now, and that gets us a triple bond. Okay, so questions about that one? Okay, cool. So I can set it up so that 1 halogen is on each carbon. I can also set it up so that they're both on the same carbon. But it's pretty much exactly the same reaction. We just have 1 halogen and 1 H leave. And then the other halogen and the other H leave. And that gets us to the same place in the long run. Okay, the one thing you might be asking is, regiochemistry-wise, like this has a pretty clear preference because there's only one place you can do both eliminations. Here, I could have picked 2 H's here, or I could have picked 2 H's here. And you might, okay, so I guess Zaitsev's rule favors the more substituted alkyne. But there's actually another factor going on here that we might have to worry about. So let's show that. Okay, so if we do okay, so same molecule, only I've now made this something with no other R groups out on the end. So we do the same reaction. We get to here. And then we do the same reaction, and we get to pretty much the equivalent, only it's a terminal alkyne. But I'm doing this in the presence of NaNH2. What do we know is going to happen differently if I've got a terminal alkyne with NaNH2 versus an internal alkyne? Like, it's going to deprotonate it, right? And the thing is that the deprotonation, like acid-base steps, are always faster and easier than any other sort of reaction we can do, just because you don't really have to worry so much about sterics, and also it turns out the activation energy is quite a bit lower. So if an acid-base reaction is favorable, it's always going to happen faster than whatever else is going on. So whether we want it to or not, third equivalent of NaNH2 is going to come in, turn that into the acetylide. And if we try to limit this by throttling down how much NaNH2 there is in the reaction, we're not going to stop this. We're just going to stop some other molecules from actually entering the reaction sequence in the first place. Okay, so this is actually going to be a potential side reaction for this one, because here you could do the elimination out to the end, get the terminal alkyne by mistake. So really, I might have to go through and update the notes. For now, I'm just going to go in and write a bunch of R's sneakily at the ends of these bonds so that we don't have to worry about terminal alkynes becoming an issue. Okay. So if we get the acetylide here, that may actually be useful, because maybe what we wanted was the alkyne, the acetylide here, so we could go in and start doing SN2 or epoxide ring opening or whatever. Let me just write it at the bottom. Or if we just want the regular alkyne, we don't want it to go attack anything, at this point we can just stick the proton back on there, and we would do that by an acidic workup, so H3O+. That says workup WKUP, but if we do the workup, we're just going to stick the proton back on there and get to the neutral alkyne again. Okay, so because if I didn't, if they were just straight up methyls, then I could potentially have done the elimination like out to this right carbon on the end, and then I would be getting a terminal alkyne, and then I'd have to worry about this nonsense down the bottom. Yeah, so I'm just kind of blocking that off potentially as a side reaction. Yeah? Does it matter which H or which hydrogen you choose? No, so either one. And actually, that's actually a really good point, because there's a side note about this, and that is I was real ambiguous about whether I'm getting like the cis or the trans alkene here, which might sound kind of weird, because we know from E2 reactions it's got to be antiplanar geometry, right? Like the H and the Br have to be in the same plane but pointing opposite directions. Turns out that for this like E2 kind of fake elimination I'm doing in the second step here, that actually doesn't matter. Like this can be antiplanar where they're pointing opposite directions, or it can be synplanar, like I could have the H and the Br on the same face, but they're still locked in the same plane, and so it still works. So that's why I'm kind of like, this is not exactly E2, but it's similar. So geometry is a little bit more flexible here. If a bulky base was used, would that form a diene for the first one? Good question. So I think if you look at the bond energy for, okay, so we're getting into this actually in chapter 15, but that's called cumulated dienes, where they're like right next to each other. Those tend to actually be quite a bit less stable than the alkynes, so I think they're just unfavorable enough that they don't form. I don't know if you could like force that to happen if you give it something that really doesn't want to do the double elimination in one place, but my guess is probably if it did, it would just do like a proton transfer and rearrange itself as soon as you gave it free rein anyway. So yeah, good question. Okay, so other questions about this? Okay, cool. So the reason I'm covering this now is because this actually affords us a way to move the camera over. There. Okay, so we've covered ways to get from the alkyne to the alkene, but this actually lets us get from the alkene to the alkyne by a couple steps. So I'm going to draw like a slightly simpler version than what I have in the notes just to save space. But as long as we can take our alkene here and get a couple of bromines onto the carbons, either both on the same carbon or one onto each. That'll get us to here. And now we have a setup going such that we can do a double E2 across the middle. And get an alkyne here. Okay. So this is kind of a short snippet of a synthesis, but this is kind of a way to increase the number of carbon-carbon double bonds if we want to go alkene to alkyne. Okay, so questions about that one? Sorry, yeah, okay. Okay, cool. Alrighty, so what I'm going to do now is sort of a longer synthesis problem that uses a lot of the chapter 14 stuff and kind of puts it together. Okay. So here is a synthesis practice problem. Okay, and we are trying to make that from just acetylene itself, plus any other reagents that we need. Okay, so I'm not sure if all you guys saw this, but this arrow means working backwards. I don't remember if I reviewed this in week 1 either, but basically this double bar arrow here means make this from. So make this complicated molecule from this thing. So we could just as well have written this as just a regular arrow going the opposite direction, turn this into that thing. So that's a retrosynthetic arrow. Okay, so looking at this and trying to figure out how to pick it apart, the epoxide functional group here, I really only know one good precursor to what I could have used for that, which is the alkene. So pretty much I'm going to redraw this thing down here. The alkene. And then if I want, I can draw the H's, although I don't have to. Okay, so this I know how to turn into that. Quick check on the stereochemistry here. I know that when I make the epoxide, the groups that were cis to each other in the alkene stay cis in the epoxide. So that's kind of why I set it up as the cis alkene here. Both the R groups coming off there need to stay on the same face of the epoxide that I made. Okay, reagents for that. MCPBA, good, yep. PBA. There's other ways to do it too, but like we could do halohydrin formation and then convert it over, but this is the easiest way. Okay, and I guess like you could write just any other peroxy acid like RCO3H or whatever, but that's probably what you would use when you're doing it in the actual lab. Actually, I guess you guys who are taking lab, that's what you're doing this week, is using MCPBA. Okay, so we know that we're coming from an alkene. I guess we haven't actually taken a step back, like this is something you might want to do earlier on, but figuring out which carbons of our starting material become which carbons of our actual final product is also a good thing to check at some point. Just from looking at this, probably the easiest option is we could technically have them end up anywhere, but the easiest option is have them be the 2 carbons of whatever functional group that we have around. So probably this chunk is going to come from that chunk as the easiest way to get stuff put together. Okay, so if we assume that that's how we're doing it, probably working backwards from here, the best immediate precursor is just to come straight from the alkyne before this step. So we could have, before this, come from this alkyne. Okay, reagents to make that happen? Yep, so H2 and Lindlar. Because if we use palladium or platinum, we're going to overshoot on the hydrogenation and go straight to the alkane. So we want to make sure we get just the cis alkene here. If we're going for the trans alkene, which would also be like not this particular problem, but I could have asked you for the opposite geometry on the epoxide, and in that case would have to come from the trans alkene, so then we'd use sodium and ammonia to make that. Okay, so H2 and Lindlar. And now we've got our alkyne here, and we just have to put the two parts together on either side of it. So we can start working backwards from there. So doesn't actually matter which side we stick on first. Maybe let's do this disconnect, working backwards. So that would get us to this, and then we have to stick that alkyl group on as NaNH2, and then methyl bromide, because this is just a methyl group, a CH3. So I guess you could write it as MEBr or CH3Br or line Br, however you want to write that. Okay, so that's got one of our disconnects sort of picked apart. And then we would just have to do the other side, snip that apart, working backwards. That gets us to this alkyne, and the steps to put that on are first NaNH2, and then basically this entire chunk with a leaving group on there. So Br, like that. Okay, so a quick sanity check that we want to do is, does each step here make sense? So we know that for these parts to work, where we're actually assembling the carbon-carbon bonds, it has to be SN2 capable. So looking at this, okay, so we deprotonate, we do SN2 on here. Yep, that's SN2 capable. It's primary and there's no neopentyl effect. And then here, it's, yep, SN2 capable. It's methyl. That's about the best substrate you could ask for. And then H2 and Lindlar, yep, that's going to work. There's nothing else in the molecule it'll mess with. And then finally, MCPBA gets us the epoxide. So yep, that should all work okay. Question?
Is the neopentyl effect just when it's on the beta?
Yeah, and it has to specifically be like a quaternary carbon there, so like phenyl doesn't count because it's sort of a lot more held together and less branchy, I guess. Yep. I think I saw another hand go up over this corner. Yeah.
If you're adding two different bar groups, actually like only add one to one side of the product.
Yeah, and so let me actually go into that a little bit more because I got a couple of questions about it last time, and I'd like to kind of explain why it doesn't add two at once. So if you start out with this alkyne here, and you hit it with NaNH2, you're going to deprotonate one side first and get one of the H's off there. So if we wanted to add two R groups at once, we would have to basically double deprotonate it, which would get us to this, which looks extremely unhappy. That actually looks like kind of a crying, frowny face. But But yeah, having two negative charges on carbons right next to each other is just not anything the molecule will do if it can possibly avoid it. Okay, so it's pretty much only going to deprotonate one end at a time, so there's only one place you can do SN2 onto at a time. And so then if you want to alkylate or stick an R group onto both ends, you can do it in 2 subsequent cycles. So, okay, questions about that? Alrighty, so that's all I have for the chapter 14 notes. So at this point, I would start chapter 15, only I didn't actually finalize the notes for it. I do have the old notes posted online, and I didn't bring my phone because I sort of ran in from the bus, which was running a little late on the snow. Sweet, that is exactly what I was about to ask.
For sure.
Thank you so much.
Oh, they're not posted.
No, so if you go to lecture courses and then chapter reviews, yeah, I got the old version up, so I'll start in on that. Thank you so much,
You're welcome.
lifesaver. All right, so sorry for kind of the slapdash last minute thing, guys. All right, so I don't have the updated version of the notes for this year posted, but I guess if you go to the lecture drop down on the OrgChem website, I have sort of a link to the Loudon reviews page, which has all of the old versions on there, and that's going to be what I'll start lecturing off now, and then I'll post the updated version as soon as I can after this lecture, probably later this morning. Okay. So chapter 15 is dienes and aromaticity. Okay. So this is actually getting back into the question that was asked just a few minutes ago about could you make something with a diene when you do this double elimination. It turns out that, so I guess we'll spend a little while talking about dienes first and then get into aromaticity. So there's multiple ways to have double bonds set up in a molecule if you've got multiple double bonds. Okay, so one option is to have them sort of spaced out from each other. So these are called isolated or regular dienes. These pretty much just behave exactly what you'd expect for an alkene. Sorry, I moved that. Each of these is just going to go through exactly the same reactivity as it would if it were doing chapter 4 and 5 stuff. However, if we scooch them one closer together in the chain, so like this, now what we have is conjugated dienes. Or I guess conjugated alkenes, depending on how many we have. So these, as it turns out, are going to be actually more stable than regular alkenes, and they're also going to react differently. And then the third option is scooch them a little closer still. And here we're actually going to have to draw them differently. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so notice that the carbon in the middle here, it has 2 separate pi bonds coming off of each other. So this is actually an sp hybridized carbon in the middle. if I drew it like the regular zigzag style, then I just have two double bonds like ending up right next to each other, and so you couldn't actually tell that there was a carbon in the middle. So traditionally people sort of draw a break in the lines and then draw a little dot in there to indicate that's a carbon. These are called cumulated dienes. And these are actually less stable. And in fact, a lot of the time they're unstable enough that they don't really hang around for very long unless you're very careful and keep them at low temperatures. So we won't actually cover really anything to do with reactivity here. So they're too reactive to be useful most of the time. Turns out you can actually do some chemistry with them if you sort of make them and then immediately have them go do something else. But we're not going to be focusing on them as like a viable intermediate. Okay. So conjugated alkenes are what most of this chapter is going to be about, at least until we get into aromaticity. So we're going to look at, first of all, what makes them more stable, and then also how do they react differently. Okay. So I guess any questions about this part, first of all? Okay, cool. Okay, so what's going on molecular orbital-wise with conjugated dienes? A lot of people just winced when they heard that, I think. Okay, so I guess the big difference between isolated versus conjugated dienes is every carbon along the chain of the alkenes has some involvement in the pi system. It's got a pi bond coming off of it. So in other words, if we draw, say, this, so we don't have a special nomenclature section for this chapter, at least for the dienes, because naming these is covered already under the regular alkene names that we learned back in OChem 1. But for example, this one would be 1, 2, 3, 4, so butadiene. And then alkenes start at carbons 1 and 3, so 1,3-butadiene. We're actually going to be hearing a lot more from this one because it turns out that there's some reactions that are very specific to dienes, conjugated dienes, that this is like a good model for. Okay, so 1,3-butadiene here. If we actually draw out the orbitals on it, and specifically the pi orbitals, we've got, I guess not the pi orbitals, but what I'm going to draw is like the unhybridized p orbitals. So every carbon is sp2 hybridized, and with an unmixed p orbital. Which is what it uses to make its pi bonds. So this double bond here is made from the overlap of these two p orbitals. We can show those kind of blending together at top and bottom. And then also down here, the same thing's going on. These two p orbitals blending together at top and bottom to make another pi bond. But even though this is where the pi bonds officially are located, we still have pi orbitals, or we still have p orbitals that are on these two adjacent carbons in the middle. And so we can also, even though there's no official bond between them, get some orbital overlap going on across the middle here. It's weaker, but there's still some kind of contact between the orbitals there, so that they're gaining stability by slightly merging together at the middle of the molecule. So, even though it's officially a single bond, it still acts just a little bit like a double bond. So we're used to seeing cases where the single bonds are freely rotating and the double bonds are locked forever in the same conformation. Here it's not quite so clear cut. The single bond in the middle has a little bit more barrier to rotation than a regular single bond would have. So this molecule is going to prefer to be in one of two conformations. It's going to prefer to be either all coplanar curled up into a C shape. And the way that we describe this is, if we treat this single bond as if it were a double bond, so if we pretend that's a double bond, would this double bond be a cis or a trans alkene in the middle? It's cis, right? Across this thing. So it's not really a cis alkene in the middle here. We're going to call it S-cis because it's a single bond. Or we could do it the way that it is up there, this kind of zigzag shape. This is called S-trans. So it can still interconvert freely between these, but it's going to strongly prefer sitting in one shape or the other the majority of the time. And that's because as long as it's in either the S-cis or the S-trans, then everything is coplanar, and it can take advantage of this overlap across the middle of the molecule. As soon as you get the two ends of it sort of not coplanar, where they're like perpendicular or somewhere in between, then it loses that energy stabilization. And so it's got sort of a penalty for going out of plane, even if it's only for a little bit. So it sort of has the two states that it can click back and forth between and spends most of its time there. Okay, there is one problem about the S-cis form, however, and that is kind of for the same reason that cis alkenes were unstable relative to trans alkenes just because of sterics. We have the same thing going on here. So if we do like a little bit closer look at what's going on here, because both of these alkenes have something pointing off into the middle. The molecule I'm looking at right now, they're just H's. I think I used this sort of description when I was doing OChem 1 last semester, but I'm not sure which other lecturers do, but this is kind of the way to show, like, here's like a big spherical thing with its own electron density, here's a spherical thing with its own electron density, and they're like trying to cram into the same space and impinge on each other's personal space, I guess. So there's steric clash between the H's, or steric strain. And so really this thing is, even though it wants to get as coplanar as it can for orbital reasons, it's getting nudged slightly away from that state for steric reasons. So this is kind of an electronics versus sterics kind of conflict. And so really it's going to pop out just slightly out of plane. So So really, how do I draw it? Okay, so this is kind of awkward looking, but especially since it's a double bond, but one of the alkene parts is going to twist slightly into the page, and the other part is going to twist slightly out of the page so that the H's aren't quite crammed into the same region. All right, so the exact angle that they rotate to kind of depends on where the minimum of the energy curve is. Like, you're sort of got competing effects. Electronics wants it to be all in plane, sterics wants it to be out of plane. And the exact angle that they rotate to kind of depends on, I guess, how bulky the H's, or how bulky these groups in the middle are here. So if it's just H's, it's probably going to be pretty close to coplanar. But if you try sticking a couple of, say, terbutyl groups on there, like, no way are you getting that all even close to coplanar. And then electronically, this would be probably pretty unlikely to be in this conformation. Probably it would spend most of its time S-trans if you had a bunch of bulky R groups here. Okay, so questions about that? Okay, cool. So this is going to be actually crucially important when we start looking at a reaction where the molecule needs to be S-cis for it to work. But we'll get to that in a little bit. First, we're going to look at cumulated dienes. Okay. Actually, okay, cool. So I've got like 4 minutes, which is just all the time I need to cover all we're going to see of cumulated dienes. Okay. So these things' whole deal is there's a carbon in the middle, and it's sp hybridized, and then the two on the ends are sp2. But if you remember the way the orbitals are shaped for sp hybridized carbons, it's actually the same as it was for an alkyne carbon, where you've got sort of the sigma bonds you can draw to each carbon. You've got one p orbital above and below the plane, and then you've got the other p orbital sort of in front and in back of the plane. So one of these is used to double bond over to one side. On the notes, I have that going off to the right. So here's one pi bond that you have, and then the other one has to be coplanar with the other carbon that it's double bonded to. So here's the other double bond. So basically what this means is that you're sort of putting this together from like two perpendicular planes. Like this thing has one pi bond to it that's horizontal and one that's vertical. Same as in an alkyne, only now they're going in two opposite directions. So the reason I didn't finish drawing this molecule yet is because if we're showing stereochemistry, really what you need to do is show kind of like a 90-degree twist along this molecule where one pair of H's out at one end is horizontal and the other pair is vertical. Interestingly, this actually came up in the chapter about chirality because these two groups are at 90 degrees to each other, which means as soon as you have two non-identical groups out here and also two non-identical groups out here, what you have is a molecule that's non-superimposable on its mirror image. So so if each carbon has two different groups, we're going to get, for example, so let's do a CH3 and an H to keep it simple. So like that. And that is actually not superimposable on the mirror image of itself. So here and here. All right, so I covered this briefly in OChem 1. I'm not sure if anyone else did, but model kits are super useful for seeing this if you're having a hard time with it. But basically, if we're looking at this, any one of the three carbons in this cumulated chain, if we disconnect two of the bonds and then swap them, we would convert this molecule to its opposite. And so each of the 3 carbons of the accumulated diene is actually a stereocenter. So you can sort of build a model out of it, and then if you pop off these 2 groups and flip them, you get the other molecule. Pop off these 2 groups and flip them, same thing. In the middle carbon, it's a little bit harder to see, but if you sort of disconnected both parts of this double bond and flipped this whole end of the molecule upside down, it's basically the same operation as if you just swap the 2 end groups out here. All right, so I'm going to get into some reactions of dienes next time, but I will have the notes up long before then. So, okay, thank you. Thanks.